So in this video what we are going to be seeing is, if you have a particular transmitter, an RF transmitter and a receiver, if there is a certain transmitted power of PT, we want to know how much is the received power, how much is the received power PR. So before we do that, we can look into what is called as polarization of an antenna. Here what you call is a two-wire antenna, what we call as a dipole antenna, where you have this transmission line that is essentially bent into two arms like this. This is a dipole antenna. The polarization of the electric field in this case is going to be in this particular direction, meaning that the electric field varies in this particular direction up and down. As long as the receiver antenna is also vertically aligned, then we will be able to receive a signal. So essentially the RF signal, the electric field is going to be oscillating as it propagates through, and it is going to be polarized in this direction, having the electric field vector in this direction. As long as the propagation direction K is in this direction with the electric field E pointing up, this antenna, the receiver, is going to receive it because the polarizations are matched. The same scenario, if the receiver was placed horizontally, here it is vertical, is vertical polarization. If the receiver is placed horizontally, by horizontal we mean that this receiver would be able to capture the electric field that's varying horizontally, and it won't be able to receive any vertical signals. So since the transmitter is still transmitting in vertical polarization, the waves will not be received by this receiver antenna because it is aligned horizontally. So here there is a polarization mismatch. There is a polarization mismatch. Now let's say we are matching the polarizations of the transmitter and the receiver, and the distance between the transmitter and receiver, let's say, is a distance R. It is very useful to know, to design the system parameters of what should be the transmitter power or what should be the sensitivity of the receiver, if we were to able to know what is the received power for a certain transmit power at a certain distance R. And that is what is given by what is called as a FriisTransmission equation. FriisTransmission equation. So essentially it starts with a transmit power of what is called as PT. We denote it by the symbol PT, so that is going to be in watts. If this transmitted power was transmitted by an isotropic radiator, that means it radiates equally in all directions, then if I were to place a receiver at a distance R, then at that location the power density, while I transmit PT, the power density that I receive here, that means how much watt per meter square I would be able to receive at a distance R, that is going to be my total transmit power over the surface area of the sphere of radius R. And we know that the surface area of a sphere of radius R is 4 pi R square. So this is going to be PT over 4 pi R square. So that is going to be the power density at a distance R away from the transmitter. And typically power density we're going to be denoting it by W, and let's say it's W naught, and that's going to be PT over 4 pi R square, and that's going to be watts per meter square, and that's why it's a density factor, power density. Yeah, it's watts per meter square. Now if this antenna, instead of being isotropic, if it had been a directive antenna, with a certain gain in a particular direction, a gain in the particular direction of theta comma phi, then the power density of the transmitter, still W, the power density for a directional antenna as a transmitter is going to be PT times the gain in that particular direction. The G is the gain in that particular direction over 4 pi R square. Unlike the isotropic, it's going to be W naught times G. The WT for the transmitter is going to be whatever the gain of the transmitter is, GT in this case. So this is going to be the power density of the antenna at a particular distance r when it has a certain gain and a transmit power of Pt. So note that this gain itself is direction dependent. It can be different on different directions. For example, if you see this animation, this antenna is set to radiate in this particular direction, but the receiver is at some other angle. It is at some other angle. So the gain of the antenna in this particular direction is what matters. It might have a peak gain in this direction, but that does not matter here because the receiver is at a certain other direction. So you're going to compromise this. So the received power in that sense is going to be the gain in that particular direction where the receiver is. So now if we want to know what is the, now we have seen the power density right at the receiver. The WT is the power density at the right of the receiver, which is at a distance r. Now if you want to know what is the power that is received at the terminals, we can use the so-called aperture area of the receiver antenna. We know that is going to be lambda square g over 4 pi. And the G is going to be the gain of the receiver in this case. So essentially the received power is going to be the power density due to the transmitter at the receiver at a distance r times the area of the effective area of the receiver, which is AE, and that's going to be lambda square GR over 4 pi. So if you were to plug that back in, we end up getting an expression for the received power in terms of the transmit power, gain, aperture area, and the distance. Clearly we see that the received power is going to be high if the transmit power is high, or if the transmit antenna's gain is high, or if the receiver's effective aperture is going to be high. And it's going to be inversely proportional to the distance between the antennas. That means if the distance is increased twice, then the received power goes down by a factor of 4. So it's like the square of the distance between the antenna. It's inversely proportional to the square of the distance between the two. Now the ratio, the received power over the transmit power can be expanded, and writing the aperture area in terms of the gain using this equation, we see that the received power is going to be proportional to the transmitter's gain and the receiver's gain. And we can use always the efficiency factored in terms of the directivity, since the gain is efficiency times the directivity. If the directivity information of the antenna is given, then the efficiency values can be used to figure out what is the received power for a given transmitted power. Notice that this ratio should be unitless. So this is unitless. Now if you notice this term here, this is a property of the antenna. The dr and the dt are the properties of the transmit and receive antennas. So is the efficiency. Whereas this term is a physical limit. So we can change and improve, make this value higher. But this guy is a physical limit here. For a certain distance r, you're gonna lose this much of the received. The received power is going to be this much factor less than the transmit power. It is inevitable. And that term lambda over 4 pi r the whole square is what we call as the path loss, and that is for what we call, represented by the symbol L here. We call it as the free space path loss. So this is by the physics, we can't get rid of it. While we can increase the directivities of the transmitter and the receiver to increase the received signal, we have to live with this loss that happens in free space. So since we are looking at power in dB, the free space loss is going to be minus 10 log of this whole term here. So that is going to be the expression for the free space path loss.